Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's a pleasure to have Manoj Prabhakaran visiting us today. Manoj is a professor at University of Illinois at Urbana-Champaign. He's done a lot of great work in many different areas in crypto, and is probably most well known for his work in multi-party computation. And I guess I'll be speaking about that today.
Okay, thank you. Everybody can hear me? Well, I think the mic is not on, or the speaker is not on, but okay. So this is joint work with Yuval Ishai and Eyal Kushilevitz at Technion and Rafail Ostrovsky and Amit Sahai at UCLA. I should apologize if the slides are too verbose, and I made them yesterday night, so hopefully it will be intelligible. Okay, so let me start by reminding you of Yao's garbled circuit construction for secure multi-party computation. This is a construction which allows a party Alice. It's a two-party setting. Alice can compute f of x, y, where she holds the input x and Bob holds the input y. And it's secure in the sense that Alice learns nothing other than f of x, y, nothing about y other than f of x, y, and Bob learns nothing at all about x. Okay. The garbled circuit construction involves, or the protocol involves, the use of an oblivious transfer primitive. So let's take it as an ideal box right now. Everybody knows what oblivious transfer is here. Okay. So what Bob does, so this is Bob, that's Alice. What Bob does is construct a garbled circuit which somehow encodes his input y and send it to Alice. Alice, in addition, picks up some keys using the oblivious transfer. So Bob doesn't know what Alice's input is, but he gives keys for all possible inputs, and Alice will pick up the appropriate keys based on her input. Bob doesn't get to know what she picked up because it's oblivious transfer. And once she gets the keys and the garbled circuit, she can do a computation and find out exactly f of x, y, and nothing else. I'll come back to this construction later and describe the details more, but I just wanted to show this right now to describe the problem. And this construction is very nice. It's one of the earliest secure computation protocols. It's very lightweight in some sense, and it uses a pseudorandom generator, but uses it in a black box manner. So it doesn't matter how you implement the PRG. The construction doesn't need to know that. It just accesses the PRG in a black box manner. Okay, in addition to using the oblivious transfer, and there are no other computational assumptions needed. And if you don't like this oblivious transfer, you can, as a ideal black box, you can actually implement it using several protocols. If you implement it using a two-round protocol in which Alice first sends out the message and then Bob responds, and all you need is security against passive adversaries in this case, then what you get is a two-round protocol. A two-round protocol in the sense that Alice first publishes her some sort of a code which encodes x. Bob looks at that and sends sends a message which involves the second message of the oblivious transfer and the garbled circuit, and then Alice can do the computation. Okay, so once Alice publishes her encoding of x, Bob can transfer f of x, y to her, and Bob can do this many times for different y's if he wants. Okay, that's the setting of Yao's garbled circuit. The only disadvantage of Yao's garbled circuit is that this is secure only assuming the parties follow the protocol honestly. Okay, so security relies on the parties being honest. So then it guarantees that even if they are curious, they don't learn anything more. So our problem that we are looking at, one way to think about it, is to get the same result, get something as good as Yao's garbled circuit in its functionality, but something that is secure against active adversaries also. Okay, and in doing so, we will pay some there will be some cost in terms of extra communication and cryptographic costs, so to speak, extra use of pseudorandom generator, but we'd like to minimize that. Okay, we'd like to minimize this overhead. Okay, so we've a little more formally we define this primitive called NISC or NISC or not NISC, non-interactive secure computation. I say /OT to mean this is the NISC given an OT, so it's done on top of an OT channel. Okay. So here is the description of what a NISC OT should do. Its functionality. Now I'm describing the single instance version where Alice wants to compute f of xy only for one y. So she will so to the functionality, as an ideal functionality, Alice and Bob have their inputs x and y that they give to the functionality, and the functionality should return f of xy to Alice and nothing to Bob. This of course does allow there is room for Alice or Bob to abort the computation if they want, but the abort should be independent of the other party's input. Okay. Okay. That's the functionality. If you want to implement this, we require that your protocol has a particular structure, namely it be non-interactive. What exactly do we mean by that? So there's only one round essentially in which Alice and Bob will invoke this oblivious transfer, and it's all this. It can invoke several instances, so several bits can be transferred, but all this should be done in parallel, in the sense that Alice in particular has to. So Alice will be the receiver in all these instances of oblivious transfer. Alice will have to give her inputs to OT without seeing the outputs from the other instances of OT. Right? So she essentially gives all her inputs to OT and gets all the outputs, and then she just computes locally. Okay. I didn't, in the previous description, I also had Bob sends a message, but that's subsumed by this. You can send the message through oblivious transfer. But if you want, you can explicitly allow that Bob can send a message in addition to this parallel OT. Okay? And at the end of the computation, Alice should get f of xy. That's the structure of the protocol. The security, there is a standard way to define security. We will define, we will require that this is secure in the sense of universally composable security against active corruption. So that's the main thing for us. It's secure against active corruption. For NISC OT, you require security to hold in the OT hybrid model. Namely, in the ideal world, in the world where you define the protocol, you are given an ideal oblivious transfer primitive. Okay, so I won't go into the details of how you define security. It's fairly standard. So that's NISC over OT. You could also think about NISC over any functionality H, where the functionality is like OT in the sense that both parties give one shot input and just one of the parties, namely Alice, gets the output. Okay. Why do we do this? Not just because we can, but we will use these kind of things as intermediate primitives for different H's. Okay. You might wonder what's the point of just doing NISC over OT if you want to implement it in real life. Where do you get the OT instances? Well, just like we said in the previous slide for YaoGFS, if you have a 2-round OT protocol, you can replace this OT access by that 2-round protocol, and still the compose protocol will be non-interactive in the sense that Alice publishes something and then Bob can respond. Okay. Do we have such a thing for UC security? We know that all have this construction for oblivious transfer in the CRS hybrid model, where parties have access to a common random string. Okay, and that's a universal UC secure protocol. Okay, so if you have NISC over OT, that's as good as having NISC with just standard setup like common random string. Okay, so in the rest of the talk, mostly my goal will just be to get NISC OT, and if you and it gives a clean model of defining the problem. Okay, so that we don't have to worry about how to implement the OT itself. Yeah.
So you're going to deal with static corruptions.
The corruptions are static. There are two parties, and I'll either consider Alice is corrupt or Bob is corrupt.
Right, but the corruption cannot happen
after the protocol. Or yeah, I mean, there are not many steps. I would suspect. So you are asking if both parties are honest in the beginning and then you corrupt Bob.
Then I see one of the messages and then I decide to corrupt either Alice or Bob.
Yeah, as in you might want to actually corrupt Bob. I would imagine it's to Bob has to explain the garbled circuit. That might cause some problems. I'm not entirely sure. I haven't thought of it. Sometimes it does create problems. I'm too sleep deprived to give a sensible answer at this time. Okay. So we'll since NISC/OT is what we are looking for, I'll just sometimes call it NISC for avoiding clutter in some slides. Okay, so what are the results we already know? It's not a new problem in some sense, right? Secure computation has been around for a long time and some of it has been non-interactive. And we are interested in NISC for general functions. By general, I mean anything that you can compute in polynomial time, okay? So if you're only worried about passive adversaries, both parties follow the protocol honestly, or even if you are worried about Alice being actively corrupt, Alice, the receiver is actively corrupt, then Yao's garbled circuit is good enough. Okay, so the protocol we give for, the protocol I mentioned in the beginning, I said it's secure if you assume passive adversaries. So it's passive, semi-honest, honest but curious. They all mean the same thing, and I unfortunately use all of them in these slides. In that setting, Yao, that's the setting in which Yao proved security, or Yao's protocol is proven to be secure, but it works without much extra effort, even when only Alice could be actively corrupt. Okay, so yeah, there we know the solution. And if you don't, as I said before, it's NISC over OT, but you can change into plain model by implementing OT by a two-round protocol. Another option, which has become recently available, is using fully homomorphic encryption. Okay, and it's in some sense much better than using Yao's garbled circuit in the sense that the communication depends only on the size of the inputs, not on the size of the circuit for computation. So in principle, asymptotically, that might be a better solution, but as of now, it's still very impractical because the computation involved is too much. Okay. So these are both, only if you are worried only about passive adversary. Yeah.
So does that solution, does homomorphic encryption work even if one of the parties is
actively corrupt?
Actively corrupt?
If Alice is actively corrupt,
Alice is who's Alice?
Alice is the receiver. So in all my pictures, that party gets the output. Okay. So if Alice is corrupt, she will do the look. Okay. I'm not entire. I mean, you could. Bob can decrypt and check some MAC or something. So I don't know. I haven't thought about it. Okay. But yeah. Okay. But the point is, these are not good enough if you are worried about an active adversary, or even if just Bob could be actively corrupt. Okay, which is our setting. So what can you do if Bob is actively corrupt? Well, one is you could use a standard cryptographic tool, namely you compile a passive secure protocol using a zero knowledge proof and get an active protocol which is secure against active corruption. We want it to be non-interactive, no problem. You do have non-interactive zero knowledge. Okay, so this is one option. Bob will not only give the garbled circuit, but use the NISC to prove non-interactive zero knowledge proof to prove that the garbled circuit was constructed correctly. The trouble with this solution is, one is that it's expensive. You have to prove a very general statement in zero knowledge. And the other more qualitative problem is that it ends up using the pseudorandom generator in a non-black box way. Why is that? Yao's garbled circuit consists of use of pseudorandom generator. It says I make this query to invoke the pseudorandom generator with this input, with the seed I get that output. Now you need to prove all those things using your NISC proof. So you need to actually talk about the code of the PRG, right? So that's a qualitative problem with this solution. Another solution, which I bet none of you have seen, it's in the full version of the paper with Yuval and Amit. So we had other results in this paper, but one of the results we mentioned, and it's developed in the appendix of the full version, if you bother to look it up, is actually a solution for non-interactive secure computation that is secure against active corruption. Okay, so in some sense it's done. The problem I stated in the beginning has been solved in that result. But why is that not good enough is that again it ends up using the PRG in a non-black box fashion. It does not use zero knowledge proofs in this sense, but if you're familiar with it, it will have some sort of a multi-party computation in the head, and this multi-party computation will have the pseudorandom generator inside it. So you end up using the pseudorandom generator in a non-black box way. So that solution is also not good enough for us. Okay, so presumably I'll say we do get this, right? So before that, before I tell you that we actually get a scheme where the PRG is used in black box fashion, you might very well ask, maybe you don't need to use the PRG at all. So this is non-interactive secure computation given oblivious transfer. So we know that given oblivious transfer, you don't need any other computational assumption. You can do secure computation. Okay. The catch is we want to do it non-interactively. Okay. So we really don't know if this is possible. So in principle, it's possible that you don't need any other computational assumption to do non-interactive secure computation once you are given this OT black box. But we don't know. That's an open problem.
I don't understand the question. So given OT, you have pseudorandom generator. I can construct a pseudorandom.
No, what I meant was given the OT functionality as a black box, as an ideal functionality, not as a protocol.
Right, so
against computationally unbounded players, you can get non-interactive secure computation.
Right, but assume for a moment that you could do IPS08 with black box use of PRG.
So this does require computational assumption that PRG exists. If you're computationally unbounded, this solution won't work. Okay. Yeah. So before I switch to a question of black box use of PRG, this is another question you should ask. Maybe all this use of PRG is superfluous. It could very well be. At this point, we don't know. It'll be good to show an impossibility also there. What we will do today is to get this non-interactive secure computation on top of OT using a pseudorandom generator as a black box. Okay. In addition to this feasibility result, our construction is fairly efficient in an asymptotic sense. Namely, if you're evaluating a very large circuit, the overhead is what you're worried about is the size of the circuit times some quantity plus some additional quantity. You're worried about the quantity that's multiplied to the size of the circuit because you think of the size of the circuit as huge. Okay, so in that setting, what we can get is an overhead in terms of overhead over Yao's garbled circuit, which is a polylog of the security parameter. So this kappa is a statistical security parameter. We'll require security which is 2 to the minus kappa. Okay, so error in simulation and so forth should be 2 to the minus kappa. Then the overhead that we get is polylog kappa. In particular, the number of PRG calls that we make, okay, will be only polylog kappa per gate of the circuit. Okay, previous solutions needed at least omega k. Okay, so in that, yeah.
Polynomial, what order? What degree?
Polynomial, the actual polynomial depends on some of the components we use. And I wouldn't exactly know what that polynomial is. Okay. Yeah, it's I'll have to look up those papers or ask my co-authors who wrote those papers about what exactly is the polynomial in that. So this take it just as a theoretical, asymptotic improvement. We also have protocols which I'll mention when we get to it, which are asymptotically less efficient but maybe much more practical. It doesn't go through these complicated underlying protocols. Okay, we also have a relaxed notion of security. I'll tell you what it is in a second. And then we don't even need, we can get a constant number of PRG calls per gate of the circuit, okay, plus some additional, order additional poly kappa queries overall. But if the circuit is very large, it will be constant per gate of the circuit. And one more thing, which I won't have time to get back to, is I presented all this for single use, right? When Alice just sends out one encoding of x once, and she just gets one message from Bob and computes f of xy. You could ask, okay, maybe she wants to compute f of xy for different values of y. So she just publishes her kind of public key that encodes her input, and then different Bobs can send her different messages for each of their y's, and Alice can decode f of xy for each of those y's. Yao's garbled circuit does work in that setting. We could also get something like that, except there's a price to pay. If you want to do more of this reusing, your public key will grow slightly. Of course, it will be trivial to say public key grows linearly in the number of reuses. I'll just publish different public keys. Oh, so you're asking you are wondering what is the issue, right? Why?
No, I answer the issue. But what does growing slightly mean?
So instead of kappa, you will need something like kappa plus t if you want to use t times.
But that's linear in t, right? So if you want to reuse t times, you have
it won't be kappa times. So if originally it was something like some function of kappa, it will be now.
Okay. Current NSA and NISC numbers, standard kappa is 112. You can reuse 100 times before you double the cost. Is that a good number?
Yeah, I mean, I have no idea if you implement these things, the standard security parameters would still hold good. But yeah, that is so that will be the case. Yeah. Okay, so these are the results I want to kind of try and present today. Okay, as much as I can. So remember, we are going to get a NISC OT that uses PRG as a black box. Before I get there, there's something I'll call predicated abort security. Sometimes I call it input dependent abort security. So what exactly do I mean by that? It's an intermediate security notion that I'll use to bootstrap to get full security, but it's also useful presumably by itself. So what it says is that Bob can, so I said Bob can make Alice abort, right? He can send a garbled circuit, doesn't some junk garbled circuit, and Alice has no choice but to abort. That's fine. He is making Alice abort independent of her input. He doesn't know anything about her input. But what we will allow in predicated abort is that he can make the abort depend on Alice's input. He will still not find out anything about Alice's input. He will not. So you can specify predicate P. He will not find out if P of x equal to 1 or not. But if P of x equal to 1, then Alice will abort, and otherwise not. So if he could find out if Alice aborted, then he will learn this P of x. Okay, so it's not a safe thing to do. In particular, this won't be a UC secure implementation of the original functionality we are interested in. However, you can define a weakened functionality which actually allows Bob to do this. Okay? And you could imagine in some settings, especially if it's being used in a bigger protocol where the environment is kind of safe, this could be useful. So that's a notion, that's an intermediate, it's a relaxed security notion. We will use two specific relaxations in our constructions. One is called input value disjunction predicate. So I'll use two predicates. One is input value disjunction predicate. So Alice's input is a bunch of bits, and I can specify, the predicate P can specify a subset of these bits and values for them. Okay, so it might say x1 equal to 0 and x3 equal to 1. Or x3 equal to 1. If that disjunction, if x1 equal to 0 or x3 equal to 1, then the predicate becomes true. Okay, so that will be the input value disjunction predicate. Okay, so essentially we allow Bob to guess one of several bits, as many, not one of. He can kind of make many guesses about the different bits. If even one of those guesses is correct, Alice is forced to abort. Okay. Yeah.
Who picks this predicate?
Bob gets to pick the predicate.
So you design a protocol, and then when you prove security, Bob can say, well, I want this information. And
yeah, so the simulator will say, this is the predicate which I want to make Alice abort on. Okay. So the functionality allows arbitrary input value distinction. It allows arbitrary predicates of this form. Okay. Another one, a little more sophisticated, is this wire value distinction predicate. So here it is just a predicate of Alice's inputs, just completely specified in terms of inputs. Here we also talk about a circuit that evaluates f of xy. Okay, so and what Bob can specify, so the circuit is fixed by the protocol essentially. What Bob can specify is an input y for the circuit and a subset of wires in the circuit and values for those wires. Okay, so not just input wires, but arbitrary wires in the middle. So you'll say this wire takes value 0, or this wire takes value 1, or this wire value takes value 0, and so forth. And if any of those guesses match, then the predicate is true. Okay, then Alice will be foreseeable. You could imagine, so you might, just to give a flavor, it's not very useful, maybe Bob can make guesses that are correct, right? Maybe it's very easy to guess something about this wire, some wire in the circuit. That doesn't make it less secure, because if everybody knew that, if Bob already knew that that wire is going to be 0 and he guessed it is 0 and forced Alice to abort, big deal, he could have made Alice abort anyway, right? So yeah, so just bear that in mind. We'll come back to how to remedy these things. And
in some sense, it's like one bit of leakage about
yes,
about this.
It's one bit of leakage. If you do not want to include this in the functionality, you could imagine it's one bit of leakage that the protocol allows. Okay, and yeah, as I said, there's an intermediate notion, but it's useful. You could imagine it's useful in settings where the adversary will not learn whether Alice aborted or not. So, or that one bit of leak, that's to say that one bit that's leaked doesn't really reach the adversary because it's sitting inside some bigger protocol, or because Alice is going to aggregate many executions and she will take some action, and if only one of the Bobs is corrupt and others are good, maybe it won't make a difference. Okay, so there could be situations where it's useful. So we will leave it. We leave it as a. We give that definition and leave that construction for use for that others can also use. Okay, so the construction is kind of very detailed. There are several components to it. So I'll give you the roadmap and we'll see how far we can get. Okay, so step 1 is we will do this thing, the NISC. So we want to build NISC OT, okay, NISC over OT. We will construct NISC for OT for just NC0 functions. So NC0 functions are functions where each output bit depends on only a constant number of input bits. Okay, and further, we will not require full-fledged security. We will allow this input value disjunction predicated abort. Okay, so it should be certainly a simpler goal. Okay, so it's NISC or NISC OT for NC0 functions with IVD abort. To build that, we use something called a certified OT. It's a primitive, simple enough primitive that we define, and we build this. We build a NISC for this particular primitive using MVC in the head kind of idea. So I'll try to go over that in detail, and then you can combine that certified OT NISC with, essentially you could think of that also as a Yao's garbled circuit construction, which is semi-honest secure, okay, but only for NC0. So you can actually build those things without computational assumption and combine these two to get the NISC for NC0 with IVD abort. That will be our first step. I'll go over that in some detail. And the other step, main step, well, there are multiple things we could do, but they all have the same flavor. What we are going to do is create NISC schemes which use some NC0 function as, instead of OT, they will use some NC0 function. Okay, so the ideal box will evaluate some NC0 function H, okay, and give the output to Alice. And the idea is that you could use the original Yao's garbled circuit, but you have to kind of make sure that Bob doesn't cheat in that. You'll use this NC0 function to check and verify that Bob created it correctly, up to some extent. Okay, so that's kind of the idea. and I'll say why it's not that simple. In particular, this H has to be NC0, and it does not use the PRGs. Okay, as in it doesn't, you cannot use a PRG in a non-black box way. So this, whatever this H will be something which does not touch the PRG, which makes it hard to actually verify that the construction is correct. Yaw's garbled construction. Okay, we have three variants of that. First one is a very lean variant. Okay, and this is kind of our main variant. It gets only WVD abort. It's wire value distinction abort. And this one gets full-fledged security, but it won't be the most efficient one. Okay. Now these are in the NISC NC0 model. So next step is to plug in the NISC for NC0 into these constructions, and you'll get some NISC protocols, okay, NISC schemes. And it will be such that we will be careful with this so that for instance, here you take a NISC NC0 protocol. It requires NC0, no error NC0 ideal function, ideal primitive, right? But we are going to plug in something which has IVD abort. Okay, so we have to see how that affects the final security. But it's simple enough to make sure that that will show up the same way after composition. So after composition, you can still get only input value distinction abort. That is in this case. In the other two cases, the abort condition is more generous. So, so this already allows WVD abort, which is more generous than IVD abort. So you'll end up with something which gets WVD abort. And here it allows arbitrary predicated abort. So you'll end up with a NISC which has arbitrary predicated.
So what's the difference between arbitrary predicated abort and WVD abort?
So here it's arbitrary predicate of the inputs. Here it's wire value disjunction. You can specify a bunch of wires and values for them in the circuit, in the given circuit.
Specified circuit.
Yeah, so you could say the protocol comes with a particular circuit.
Okay, I see.
And that's
this is for essentially any circuit.
any predicate. Okay, not just wire value disjunction. So this is very limited. It's saying wire value disjunction. It has to say this wire takes 0 or that wire takes 1 or that wire takes 0.
For this particular circuit.
The circuit is fixed, and further, the problem is not that the circuit is, okay, that's what one thing that limits it, but also it's not an arbitrary function of the wire values, right? Then it is an arbitrary function of the inputs. And then these two schemes, this one we leave as it is. We don't know how to upgrade this to full-fledged security, but it's really lean. Okay, this is efficient. These two we will upgrade to full-fledged security. This one, as you can imagine, it has some problem with the input value distinction. By doing some sort of input encoding, we can make sure you get full-fledged security. This one, which allows you to ask questions about the circuit, we want to make sure you don't get much information by asking questions about the circuit. So we will use essentially a private circuit construction and make sure that this is harmless. Being able to use wire value disjunction abort doesn't really help you. You might just as well abort independent of the input, and that will be the full-fledged security. Okay, so okay, so we have these three constructions. This one is the most asymptotically efficient in terms the polylog k factor overhead over Yao holds for this construction. But that may not be the most efficient one, given the things that go into this private circuit construction. So for small circuits, that may not be the best thing to do. So might be, you might want to stick with this. This has an order kappa overhead, not polylog kappa. And all these constructions use the PRG in a black box. Okay, now I will try to go over as many boxes as I can in the amount of time I have. So I'll start with trying to build that, right? So you want to build NISC for just NC0 functionalities. Now here you don't need any computational assumptions. Okay, unconditionally secure constructions are known. We care only about IVD security, but even if you wanted full security, you get it. In particular, a long time back, Killian gave a construction about how to do secure multi-party, two-party computation using OT unconditionally, and it has inside it a protocol which works for NC0 and can be extended to NC1, without any computational assumptions. Okay, and it's a non-interactive protocol. Okay, the trouble is it's very inefficient, so we won't use that. But if we just wanted the feasibility result of black box PRG, we could use that. Okay, Killian's original protocol does in the paper has only IVD abort kind of or predicated abort kind of. Actually, IVD abort security, but it can be amplified to full security.
What's the idea of this this construction? You take a garbled circuit and...
No. Killian's construction doesn't have a garbled circuit, but you could, yeah. So
some kind of randomized
it's some kind of randomized encoding. Okay.
So unconditional randomized encoding.
Yeah. Since it's NC0 function, you can get a polynomial-sized unconditional randomized encoding. So yeah, Killian doesn't call it a randomized encoding, but I guess you can look at it that way. We do use that kind of more explicitly. We use, for those of you familiar with the terminology, what would be called a decomposable randomized encoding. Another way to look at it is that it's a Yao's garbled circuit specialized for NC0 functions without using pseudorandom generators for encryption. Right? You would instead use one-time pad, essentially. The one-time pads will have to grow exponentially with the depth of the circuit, but if it's NC0, you're fine. Okay, and so we'll have to build a NISC OT for certified OT. That'll be like our primitive. Once we have that, then we can compile any randomized encoding into a full-fledged NISC protocol. It'll have unconditional security. So this is kind of the main. So I'll go over both steps, but this is the main, meaty part there. And it'll be used using, it'll be realized using MPC in the head that I've been talking about. This idea of taking a unconditionally secure, sorry, not unconditional, taking a semi-secure protocol and compiling it with a certified OT functionality does extend to beyond NC0 also. But then this is not going to be unconditionally secure. You need to use PRG, and then this compilation won't use the PRG in a black box way. Okay, so if you didn't care about black box PRG, this would have been a way to get NISC OT for not just NC0 all the way. Okay, but since we want to stick to black box PRG, we don't use this. And I should mention, so both these constructions here and the one in IPS, they both build this certified OT, right? They both follow this. The difference in the two constructions is how the certified OT is built. In IPS, it has a bigger overhead, theta k overhead, kappa overhead, whereas here only we get only a polylog overhead. And the difference is the MPC that's involved in building the MPC in the head. Yeah.
Say what certified OT is?
I will.
Okay.
So yeah. Okay.
What is DIK?
So the efficiency we get, all the polylogs come from this protocol Yuval Ishai, and I don't remember the name of K. No. It's no, it's not Kushilevitz. It's a student. I think it's a student of Damgard's. It was in crypto or Eurocrypt last year. This protocol has the. So usually we think about the communication complexity in protocols, and we try to minimize that. This protocol minimizes also the effort, the work, the total computation done, and in particular the views of the parties. That will be polylog kappa, the overhead per gate. Okay, so that's where some of our efficiency comes from. Okay, so I should describe what certified OT is. So in certified OT, there is a it's parameterized by a predicate again, call it pcert, That's the certificate predicate. It's fixed for the functionality. The sender inputs a bunch of pairs of strings. Okay, so for I equal to 1 to L, it will input SI0 and SI1. So these are presumably for doing OT. In addition, it can present a witness to the functionality, W. The receiver wants to pick up, wants to do OT on these strings. So it has bits, choice bits B1 to BL. What does the receiver get? Well, it will get these bits that it asked for. So SIBI, right? It will get those bits. In addition, it will get this, you'll evaluate the certificate or the predicate and say whether W proves that S has the property. S is all the inputs that the sender has input. Okay, so why would this be useful? This is like you're presenting something about the garbled circuit, and this predicate can actually check if the garbled circuit is constructed correctly up to some. I'll say how exactly we use it, but that's the idea. Certified OT can not just give you the stuff you picked up. So remember, you don't see, as a receiver, you don't see all of the set S. So you cannot really check, if some property holds for the entire set of inputs, right? So this is, the certified OT will do it for you. It can check if, whatever property you're interested in holds for the entire set of inputs. Does that make sense?
You're thinking of this SIs as like the entire garbled circuit essentially.
Will be, yeah.
What is W?
So you'll use randomness to build this garbled circuit, not just the stuff you send. So there will be not. So these would be the keys in the garbled circuit, but you'll actually present more things to the certified OT functionality. Okay. In particular, certified OT functionality is not going to make any PRG calls. So you have to present the PRG values. Okay, so how do we realize? So this is the certified OT functionality. Okay, how do we realize this? Is we take an MPC, consider an MPC functionality which is defined on a large number of parties. Okay, so there is one party which we'll call the sender. So this is just something that will be run in the head, right? So it will never be actually implemented. There will be so there can be more than two parties, a lot of parties. There will be one sender. There will be two L receivers. L is the number of OTs you want to do. So we'll call the receivers RI0 and RI1. And there will be a large number of servers. Okay. The servers do not have inputs or outputs. The sender's input will be exactly what the certified OT will require as input. So in this MPC functionality, the sender's input is what the certified OT will require the sender to input. So this sender will be that sender. The receivers do not have any input, so it's not exactly these receivers. But instead, every receiver, RIB, gets its string. So for each of these strings, there is one designated receiver who will receive it. Okay, it will also get the certificate. Okay, so every receiver also gets this predicate, whether the condition is satisfied or not. Okay, so that's the MPC you should imagine.
When the servers don't get anything.
Servers will run the MPC protocol for you. Okay, so this is a functionality in which the servers do not do anything, but in the protocol the servers will do something. Okay, so we'll take a protocol. We'll need a protocol row for this particular functionality, and we need it to be secure against passive corruption of up to T servers. Okay, so this will be a kind of a typical MPC protocol in which the inputs are shared to the servers, but it will be sufficiently secret shared so that you take up to T servers, you don't learn anything about the inputs or the outputs. And you can also corrupt any number of clients. So if you corrupt a receiver, of course you will learn this bit, right? If you corrupt the sender, you will learn all the bits and so forth. So you can corrupt any number of clients, clients meaning the sender or the receiver, as well as up to T servers, and it will be passive secure. This is a passive corruption. Also, we need, for the same number of corruptions, up to T servers and a number of clients, we need this property of robustness. Namely, if you corrupt actively, maybe you learn things you're not supposed to learn, but you cannot change the correctness. So uncorrupted parties will get only the correct output. Okay, so we require a protocol with this kind of robustness and passive security. There are several protocols, but the one which will meet our security requirements will be this DIK protocol. Sorry, the efficiency requirements will be the DIK protocol. Okay. So how exactly is MPC in the head carried out? It's same idea as in this paper IKOS from a few years back. So all of whom are co-authors in this paper. Okay, so the sender will run this MPC in its head, the whole execution, and prepares views of all the parties. Views consist of the randomness it uses and all the messages it receives, okay, and its inputs, if it has inputs. The messages that it sends are defined by this, messages that it receives and its randomness, right? So that's its view, and this is this big network of one sender, many servers who talk to each other, and a bunch of receivers. The receivers do not talk to each other; they just talk to the servers. Let's say you need a protocol of that form, and our receiver Alice will use OT to pick up a few views. What will it pick up? First of all, it will pick up one out of every pair of such views. Ri0, Ri1, it will pick up Ribi, okay? Thereby it will learn SIBI. Also, it will pick up a bunch of server views. Okay? So each server view is picked up with probability 1 over t. Even if Alice is malicious, we want to enforce this probability, can be done using OTs. And if she detects any inconsistency between views, okay, namely, if you are honest, I picked up two servers, and if this server is honest, according to what messages it got, it should have sent this message, but this server is reporting that it received another message, that's an inconsistency, okay? So you can say this edge is inconsistent. If you see any such inconsistency, then you abort. And the MPC that we will use will be the DIK MPC. That will give us the efficiency we are looking for. Okay, why is this secure? Why is this secure? You need to consider two cases: static corruption, security against Alice. So the protocol is a private protocol. Alice picks up these T server views, but you can corrupt T servers and you don't learn anything, right? And another thing is that she might actually learn. Her inputs to these OTs is exactly her inputs to the certified OT functionality. Her inputs to the OTs in this protocol that I described is her inputs to OTs in the certified OT protocol, her inputs to certified OT functionality. So whatever she feeds is a valid input. So she cannot cheat by feeding invalid inputs. The only thing she does in this protocol, remember, is pick up a bunch of stuff using OTs, and she'll also pick up a bunch of server inputs where she doesn't have control. It's randomly 1 over t probability each server value comes to her. So she doesn't have any room for cheating, right? The servers that she picks do not reveal any information because there is privacy of the MPC protocol, and there is no other room for cheating. Okay, so
you're getting the views of a constant number of servers here, right? Because there are
okay, I said probably something wrong. You pick up essentially order T servers. The probability so that you pick up less than T servers but order T servers. Okay. Okay, security against corrupt Bob is a more interesting analysis, but I think I will skip that because it's essentially the same in IKOS, and I'm really running short of time. Look at it by saying if there are only a few inconsistencies, then it can be explained by having a few corrupt servers, and they cannot change the security. If there are many inconsistencies, then it will be caught. So that's the first thing. If there are many inconsistencies, it will be caught. If it's not caught, you can argue actually that the the abort probability can be simulated just in terms of an input value disjunction. Okay, so I'll skip that. You should believe me that that'll give us what we wanted. Okay, so all of this is just to say we can build this thing, okay, certified OT, and how to go from that to this is you start with say a perfectly secure Yao's garbled circuit protocol, and Bob needs to prove that the garbled circuit was used, prepared correctly, and for that you'll use certified OT. It's fairly straightforward. So let me actually, do you want me to go over that? So the certified OT will take, I said, so in this NISC, which is semi-honest secure, like say Yao's garbled circuit, use OT, right? Instead, people will be using the certified OT now. That in addition to that, certified OT will carry out the job of the original OT. In addition to that, it will verify that Bob created the garbled circuit correctly, right? Okay, so
since the certification for the function that you use in certified OT is the correctness function for the garbled.
Yes. So maybe one more thing to point out is this is an unconditional protocol, so there is no PRG involved in this, right? So it's a simple function saying that everything is formed correctly. And as before, Alice can't cheat. Bob, when all her inputs are valid, so we do require that this protocol to have that property that all her inputs are actually, her inputs to OT are actually her inputs to in the functionality. Okay, so Alice doesn't have room to cheat, and Bob cannot really cheat because of the certification, but he can cause input value distinction abort as before. He can cause certified OT to abort, right? Because we only have this kind of a certified OT. So that'll mean these inputs are the same. The inputs to the certified OT are the same as the inputs to the NC0 function. So this will be an IVD abort for the NC0 function also. So that's how we get this. Okay.
I don't know if you said why the certified OT protocol has this abort issue. I mean, where does it come from?
Oh,
so this previous thing.
Yeah. So okay, I can show you in a second. Because I can construct a view. Oh, okay. By the way, this bullet is slightly wrong, but it's supposed to be the same as this bullet. I forgot to change it when I edited. Okay, so this bullet, as it says, Alice picks up RIBI. So if I put in a bad RIBI, for instance, it's a bad view. You pick up, it will be inconsistent with some server, right? So you abort only if you pick this up. So I can, if you abort.
I can say, is one of them, bad or not?
For instance, yeah. Essentially, that's all you can do. That's what the proof will do. Okay. There's an error in the first bullet there, but nobody read it, so it's fine. Okay. Okay. So that's the first step. The second interesting step is how to build NISC given some NC0 functionality. Okay, so I'm kind of out of time. Is that okay? But we are just starting on the interesting part. Okay. What are we working modulo? Okay, so as I said, the idea is that these NC0 functions will help you do some sort of okay, so I'm just describing what kind of NC0 function these will be. Okay, first let me define what NISC/NC0 is. Right, there will be some function h some NC0 function, and it has to have the property that it gives outputs only to Alice. It takes inputs from both parties, gives output only to Alice, and we'll also require that Alice inputs to this NC0 function should be the same, or in our constructions, the ones where we use it, we'll require that this NC0 function takes the same input as for the functionality we are trying to achieve, right? Okay, so all these three variants use Yao's garbled circuit and something called oblivious max. So let me quickly try to recall what Yao's garbled circuit is. This slight variant from what you might have seen typically. This has also been described in the literature in this form, but it's slightly different. Okay, so this is there's a circuit C. Alice wants to learn C x of x comma y. Bob takes the circuit C, and for each wire there is a mask bit, okay, random bit, and you could now imagine a new gate functionality. When I put a prime, it means masked. When I don't have the prime, it's unmasked. Okay, so a new gate functionality of two masked bits, two masked wire values, is first you unmask them, you apply the original gate function, and then you mask it. Okay, so that's this f sub g defines the gate's functionality. It may be and, or something like that. It takes two wires and two bits and outputs one bit. And this f prime is just the in the garbled circuit, the function, the gate function. Okay, so your garbled circuit consists of tables like this. So I'll say, okay, for the gate number 1, your a prime and b prime could be 0. If it's 0 0, my c prime, the garbled output is say some value 0. I get this by unmasking a prime and b prime, applying the original function, and then masking it. Okay, and I'll do this for every gate, and that's my garbled circuit essentially. There is no garbling in Alice's input wires and also in the output wire. Okay, for those wires W, this mask, which I call R of W, is 0. Now, I'm not done, but so far, seeing only the wire values in the garbled circuit evaluation, right? I see the gate inputs and gate outputs for this garbled circuit. I don't get any information other than the output and Alice's inputs. Okay, so if I take an X and Y and evaluate the circuit, and I don't tell you what these mask bits are, all you get information theoretically is Alice inputs and the output. However, this is not all that I would see. I would typically also see the gate functions. If I get to see this table also, then we have a problem, and I can look at this and say, oh, there's only 1 1 and 3 zeros, so, and I know that this is an AND gate, then I know that this is C prime is masked with 0, bit 0, right? Things like that. So we need to keep it all encrypted. Okay, so we need to keep this C prime encrypted, but then where are the keys going to sit? They will be sitting encrypted along with A prime and B prime. Okay, so you'll need the keys also. So this is what. So if you have a gate like this, what you will keep, what you will have is for each wire there will be two keys, a 0 key and a 1 key. And what you will keep in the table, instead of just that plain C prime, what you will keep is an encryption of C prime and the wire case, the key for the wire W on the value C or C prime, doesn't matter. It's not labeled. You don't see if it is, what is the C inside. You just get a key. Okay. And this will be encrypted using the keys for the wires U and V with the values A and B. Okay. Oh, one more thing, the encryption is different for different gates. So I'll say that I'm saying there's also a tag for the encryption. More formally, it's easier to think of this encryption as using a PRF, the way you would use encryption. You do symmetric key encryption. So the key is, the key for the PRF, the seed for the PRF, and you call the PRF on the tag. So when I change a gate, I'm using a totally different set of masks, right? So to encrypt, I take the message, I mask it with both these masks. Okay, this is the encryption. instead of writing all that, I'll just denote it by this. Okay, so for the gate G and for A prime B prime, so that specifies a row in that table. I keep this entry as the last element. Okay, and the full protocol is that Alice will use her keys to pick up KW, XW for wires, W for her inputs. Okay, so she will pick up if it is 0 or 1. She'll pick up only one of the two values of KW. Bob will send the garbled circuit, so this table, and for each of his input wires, he will send its key. Okay, but looking at this key, you don't know whether it's a key for 0 or key for 1. Then Alice evaluates by decrypting the entire table, and she gets C prime and a key at each gate, and gets the output, right? As we said, the trouble is that if Bob is malicious, he can make Alice evaluate any arbitrary function. You never know what he puts in those gates. Okay, so we want to somehow use the NC0 function to check correctness. The catch is that this NC0 function should not include the PRG code. Okay, use the PRG code in a black box way, so we cannot really check if this encryption is correct, right? We don't know we cannot use the PRG code in this NC0 function. Okay, I'll get to that. It's fixed using a very simple idea, and I call it oblivious MAC, but it's a very simple idea. It's just MAC itself. But let me define oblivious MAC. So this is a primitive, again in the NISC kind of setting. Alice and Bob both have inputs, only Alice gets output. Alice's input is a key for macking, and Bob's input is a message and a tag. Okay? And what Alice gets is a receipt of the MAC. And the tag is independent of the key, so Bob can create it. It's just a random string. The obliviousness is that if the tag is chosen at random, Bob does it properly, then just the receipt by itself does not reveal anything about the message. Okay, so typically that's not the case, right? I feed a key, I get a MAC on a message. I can check if the message is exactly this message or not, right? For instance, so this randomization here is so that you don't learn anything about the message just from the receipt. But later, if I send you the message and the tag, you can verify it. Okay, that's a verification. And the unforgeability is that you cannot find two message tag pairs with different messages such that I take the receipt by macking one of them and I try to verify the other message. It shouldn't verify. Okay, it should be infeasible for you to find such a forgery. Okay, so this receipt is like a commitment to the message. You get a MAC on it, but you really don't know what the message is at this point.
It's strange to call it a MAC, right? It's more like a commitment.
Except, well, the reason it's a MAC is because it's really a MAC. You can take a one-time MAC, okay, and you MAC the message using the key, and this tag and receipt are just shares of the MAC. The only thing is the tag was chosen before the MAC was created. Okay, so it's a very simple thing. I just defined it kind of laboriously, but this is all it is. This is all we are going to use. So the receipt is just a share of the MAC on the message, but you hold only one share. The other share is with the other guy. But the point is the other share could have been chosen without knowing the MAC, right, or the key or anything. Okay. Now the first construction, first of those three constructions, but I will probably just do this one. It's a very lean construction. It gets you predicated abort only though. So I had to define, I said it's a NISC NC0, I had to define the NC0 functionality. Okay, so it takes from Bob the wire masks. Okay, that's all. It doesn't take anything about the keys. It doesn't take about any input about the PRG or anything. It just takes the wire masks, okay, of the garbled circuit that Bob is preparing, and then it can compute this bit C prime. So it can essentially compute this table, the unencrypted original table, right? And for each row in that table, it carries out an oblivious MAC on the C prime. Namely, it takes, in addition to this, it takes a tag from Bob and gives a receipt to Alice. It takes a key from Alice and gives a receipt to Alice. Okay? So each of these entries in each row, the C prime entry is MAC'd, and Alice gets a receipt for it. For each row, there is a different key that Alice will use. Okay? In addition, it will also carry out the OT's job in garbled circuit, namely, she can feed her input. Feed her inputs to the functionality and pick up the wire keys for her inputs. Okay, so that's what the NC0 function does. I said it will do a macking, right? Macking is actually very simple in this case. You are just macking one bit. An information theoretic mac of a bit is just half of the key. I'll give you the first half of the key if the bit is 0. I'll give you the second half of the key if the bit is 1. Right? And if you don't know the key, you cannot forge. So it's a one-time MAC. So it's a very simple functionality that this thing is carrying out. It's NC0, and it's pretty simple. Okay, so what does Bob do after this? Along with this accessing H, Bob will, in the clear, send the garbled circuit to Alice, and he is supposed to send. I talked about garbled circuit as having encryptions of this form, but now it will also include the tag for C prime. Okay, this is something that Bob chose, right? Bob doesn't need to talk to the functionality to get this tag. He chooses random tags. So this is the encryption that he sends in each entry of that table. This by itself is enough to ensure correctness. Okay, so in any row, if the garbled circuit, Alice decrypts it, gets some C prime, who knows? Bob may not have encrypted things correctly, whatever. She gets some C prime and tag. If they verify for this particular GA, the key for the corresponding row, the key and the receipt, if they verify, then it means that the C prime is correct. Okay, you have a negligible probability of making a forgery here. So that's all that Alice needs to ensure correctness. However, Bob can cause Alice to abort, right? He can put a wrong C prime or wrong tag, for instance. And by causing Alice to abort, he can, the abort can depend on Alice's input. Okay, but if there is no abort, then Alice is guaranteed that throughout the evaluation, the C prime. So let me say that once more. What does Alice do at every step? When Alice decrypts the garbled circuit, takes this thing out, she has a corresponding receipt, and she will verify the C prime, the tag and C prime, right? So if she never aborts, then all the wires she evaluated are actually correct throughout the execution. Okay, then the output is correct. But we get only predicated about security because the abort can depend on the inputs in a fairly complicated way. So I'll maybe skip through the next remaining slides quickly. To get to the WVD abort instead of the arbitrary predicated abort, we need to do a few modifications. One is that the functionality will now create the garbled circuit. Okay, it cannot really create the garbled circuit because it cannot access the PRF. Because we cannot use a non-black box use of the PRF. So what we'll instead do is actually ask Bob to provide it with all the relevant PRF query answers. Okay, and it will just trust those things. In addition, it won't just MAC this one bit C prime, but instead it will MAC these PRF outcomes also. Okay, and that takes care of the ability of Bob to cause arbitrary abort. He can just abort by lying about these PRF values. The garbled circuit was created by the functionality. So only thing Bob can do lie here is creating giving wrong PRF values, okay, to the functionality. That will be detected if that PRF, that particular query is recovered during the evaluation. And that corresponds to saying one row in that table was opened, which means a particular value of the, sorry, not one row. So these PRF values correspond to values of the wires. So this will correspond to saying one wire value occurred, okay, and that so abort happens if one of a set of wire values occurs. So it's a wire value distinction abort. So let me okay. So I will just show you the animations now. So we can get this NISC NC0, plug it in, everything will be the errors will propagate appropriately. So if it's an IVD, so the WVD abort subsumes IVD abort. So this is, we get NISC with WVD abort by just plugging in the NISC NC0 construction. We need to take care of these two. This is done using an input encoding. It's kind of fairly standard, but standard way in literature is inefficient. So we kind of use the hybrid way, which is like hybrid in the sense you use a short seed and like a t-wise independent generator, and that works as in it's a small encoding. And the decoding is quite efficient. Private circuits, I think I don't have time because I have like 3 slides for that. You want to ensure some sort of t-wise independence in the wires in the circuit. You cannot really get that for because in an AND gate, the inputs and the output are correlated, right? So but point is you don't really need full t-wise independence of every wires. We define something called operated t-wise independence, and you can achieve it by implementing an MPC protocol in the circuit. So this is the same way all the private circuits constructions have been, like the 2 papers before this on private circuits, right? So the same idea works, and if you use an MPC which is really efficient, the total work done should be small because circuit size blows up according to that. So the point is you can take a circuit C, compile it into a circuit C prime such that a wire value distinction abort in C prime tells you nothing about the input. It's independent of the input. So either you can force it to abort with some predetermined probability, or you cannot. You don't make it abort, right? So in the private circuit, the wire value disjunction predicate is independent of the input essentially. Okay, so and that's oops. Well, that is well. Oops. I'm trying to get to the last slide so that you can, if you have any questions. So that's the summary. We get NISC-OT, which is black box, which uses PRG in a black box way. And if you want to work on something, to think about getting it without using any PRG at all, or showing that it's impossible. Okay. All right. Thanks. Any questions? Yeah.
Clarification, is IPS already NISC or it is?
No, IPS, what you think of as the main IPS protocol is not non-interactive at all. Right? It takes an outer MPC protocol. The only things we have there are either a constant round protocol, which uses computational assumptions, or non-constant round one, which is without computational assumptions. That's the MPC outer protocol. Okay, and so the IPS gives you protocols which are not one round, not 2 rounds. Right? It's constant number of rounds, or if you use computational assumptions, are larger. In fact, they don't use PRG in a black box way.
So this work includes both run complexity and in terms of from non-black box to black box.
Yeah.
To black box.
Yeah.
It seems that for all of these contain some kind of randomized encoding, right? So So when you say statistically secure NISC, you're asking for, in some sense, you're asking for an unconditional randomized encoding.
Yeah. So this is well, unconditional. It doesn't have to be.
Actually, you know what? Let's say even semi-honest. Okay, I don't care about malicious adversaries. Let's say even honest but curious adversaries. Can we get statistically secure NISC with in the OT hybrid model?
In the OT hybrid model, no, that's an open question.
Even that is open.
Yeah. So can you get YaoGN without any assumptions once you're given OT? Yeah, that's open. So this is harder.
Right. It seems impossible.
But yeah, it'll be nice to prove it's impossible. Any other questions? Okay. Thanks for bearing with the long talk.